Okay, today we are starting new chapter, surface tension. Okay, what is surface tension? Okay, before surface tension, you have to learn about the properties of liquid. Liquid contains molecules which are in continuous motion, and intermolecular space is less but not the least. Those molecules which are close by, they try to attract each other, and if they are very close, then they will have tendency to repel. Okay, and let us check the surface molecules like this. So there is some liquid over here. We'll see the surface molecules and molecules inside the liquid. Suppose we are having a molecule over here. There is a molecule on here. This molecule experiences forces like this in all directions. It experiences this way. So all the forces are this way also. It is experiencing this way also. This way also attraction. This way also. This molecule is attracting and this molecule is attracting. This molecule is attracting and attracting. In all the directions they are attracting each other. That means all the forces are cancelling on each other. The liquid drop remains in equilibrium inside the liquid surface. But when we see at the top surface here, out here, so there is a force of attraction by this. The force of attraction is here. This molecule will be attracting like this. This molecule will attract like this way. Here we see these two are balancing each other. But what about this one? This one doesn't get balanced. So due to this force, which is acting downward towards the bulk of the liquid, towards the main volume of the liquid, this will cause the liquid surface to minimize in area, to contract in area. This tendency of minimizing or contracting in area is called surface tension, actually. And there is another thing what have we observed, that these two molecules are giving the force in this direction. This molecule attracting like this, here the molecule is attracting like this, and this one is making the surface of the liquid to behave like a stretched membrane like this. One is like, we have got a sheet or any kind of bed sheet and all, and you're stretching this way and this way, giving the two forces in the opposite direction here. That means the surface will get stretched. So the property of a liquid surface to minimize in area and to behave like a stretched membrane is called surface tension. You can write down this definition. The tendency of a liquid surface, to minimize or to contract in area, to minimize or to contract, contract, contract in area, and to behave as a stretched membrane, is called surface tension. Okay, this property or this phenomenon is called surface tension. Now there are some recent test questions based on this fact. So they ask question like this: why some insects can crawl or can walk on the surface of water without getting wet or without going inside? They can easily walk on the surface of water, but when we try to walk on it, we all get immersed in water, or we all get drowned in water. We cannot walk. But some small insects, they are able to walk over it. You know why? Because the surface of the liquid is behaving like a stretched membrane due to the surface tension. So that is the reason. Due to surface tension is giving a tension on the surface and making the liquid surface to behave as a stretched membrane. So small insect, they have got very small weight. So these two forces are also very small, but they are supporting the weight of the insect. That's why they are able to walk without the liquid surface getting ruptured or getting damaged. But when we try to walk, our weight is too much, or something heavy if you put over there, the weight is too much, then the liquid surface ruptures and the body goes down inside. So as long as the surface tension is strong enough to balance the weight of the body can can move on the surface of the liquid without getting wet or without going their legs inside the liquid surface. So that is the reason for it. Then they ask another questions like this. Parachutes, I think canvas, no parachutes and all that, the clothes, there is canvas clothes, tent also they use a parachute material here, that means canvas clothes. They have got small pores or holes are there in them, where water will be filling up and the water surface over there will behave like a stretched membrane, and further raindrops will not be able to sit inside, will not be able to go inside it. So this is also due to the surface tension. Surface tension is stretching and making the water drop which is already there in the holes, even in the umbrella, will not be allowing them to go inside, will be blocking it, will be supporting the weight of the extra raindrops. But when we pierce it, when we poke it with some bamboo stick and all, when we poke it this way, then the water seeps inside, water goes inside, comes inside. By poking it, we are rupturing the drop. That means the surface tension will not be there at all now, because we are, this molecules getting destroyed over there by poking it. So then the water will be seeping inside, because surface tension will not be able to balance the weight of this force will be rupturing the drop. That is the whole idea about it. Then they ask why raindrops are spherical in shape. Raindrops, like small raindrops, will be spherical in shape. What is the reason behind? In all geometrical figure, why the raindrops are spherical in shape? Because the liquid has tendency to minimize in area. For a given volume, it is a sphere which has the minimum area. And what is the area of the sphere formula? 4 pi r square. That is why the raindrops tends to or become spherical, small raindrops. Because for a given volume, the sphere has the minimum surface area. So every liquid due to surface tension has a tendency to minimize in area. So that is why the liquid drops are generally spherical, or raindrops, small drops are generally spherical in shape. Now another one. But the big raindrops, they are not spherical in shape, because their weight is too large that the surface tension on the liquid surface will not be holding the weight will not be able to balance the weight of the drop. That's why it will not have tendency to minimize in area, so it will not be even spherical in shape. Okay. So this all recent test question you may have based on the surface tension. But now the measurement of surface tension, how do we measure? So surface tension is actually, that the molecules, the forces are acting like, what kind of forces are there? These two forces which is making it behave like a stretched membrane. What type of forces are there? So they are the tangential force. We write here tangential force on liquid surface is proportional to the length of the imagined liquid surface. This length. There is this force, if I write F is proportional to L, the length is L, then we multiply the constant, that constant we denote by this symbol, this is called surface tension, L. Therefore we write surface tension formula is F by L. That means where sigma is called surface tension of the liquid. This is the formula of surface tension. More the length of the liquid surface, more the value of force, tangential force will be more. That means the surface tension will also be more. The surface tension formula we have F by L. What is the SI unit of surface tension? SI unit of surface tension of sigma is Newton per meter. And dimension also we can find it. Dimension of sigma will be force. Dimension of force is mlt minus 2 upon the length. Length and cancels, we get mt minus 2. The dimension of surface tension is mt to the power minus 2. Dimension. Force by length. Force, but what kind of liquid? Normal liquid does not have a length, but we have to imagine the length of the surface of the liquid. Okay. So the dimension is this and the unit is Newton per meter. This is how we measure. You can add surface tension for water. The value 7 into 10 to the power minus 2 Newton per meter. Water surface tension value is this much. 7 into 10 to the power minus 2 Newton per meter. We define surface tension in terms of work done also. Work done in surface energy. The energy of the molecule due to these forces, due to the force of surface tension is called surface energy. The energy of a liquid surface due to surface tension is called surface energy. We write like this: work done on surface energy or work done to create a surface. W is proportional to the area of the surface which is being created. So this one also we write with the equal sign, we write sigma A, or we write sigma is equal to W by A. This is also surface tension. Same. So we can give alternative definition of surface tension. We can say it is the surface energy per unit. It is the surface energy per unit area. It is the surface energy per unit area without causing any change in temperature. Temperature is constant. We are just creating a new area of it. It is the surface energy per unit area. And the SI unit, now we can add the SI unit we can add joule per meter square also can be joule per meter square. Jm minus 2. So we can express either of the way, Newton per meter or joule per meter square. Both of them are same only. If you find the dimension, it will come to the same. So this is also the formula of surface tension in terms of work done or in terms of surface energy. We can say surface tension is the amount of work done to create a surface per unit area. That we also can say. We can surface energy per unit area also we can say the definition of surface tension. Okay, now next topic you have to know is angle of contact. Denoted by theta. So this thing especially happens when a solid is immersed in a liquid. So for example, suppose we are having some container here in which there is some liquid. Let us have a solid. This solid can be a piece of glass, can be anything else like this. Okay. Angle of contact. This is the point of contact of the solid and the liquid. Here is the point of contact. So we see whenever a liquid is immersed in a solid is immersed in a liquid. At the interface over here at the top level, you will find either a concave shape is formed like this, or it may be a convex shape like this. Any of this kind of shape is formed at the contact point here between the liquid and the solid point. So, what is the angle of contact? Angle of contact is the angle between the solid and the tangential line drawn on the tangential plane on the liquid surface. Like tangent, you draw tangent on tangent. between the solid and the tangential plane, this angle is called theta. This angle is called theta, or angle of contact. What is the angle of contact? We say it is the angle between the solid. It is the angle between the solid and the tangential plane of liquid surface. Tangential plane of the liquid surface. This angle is called theta. Theta is angle of contact. Similarly, if we have a liquid like this, there is some liquid here, and the solid is immersed in this direction like this. But now here we have this kind of shape form, this kind of curve form here like this. So what is the angle of contact? We draw tangent on this. Tangent on this will be drawn like this. So this angle is the angle of contact. Here is this theta is the angle of contact. So angle of contact is the angle between the solid and the tangential plane. Means there will be a curve over here formed. So we have to draw a tangent on that curve, and the angle between the solid and the tangent drawn on the curve is called angle of contact. That is denoted by the symbol theta. Okay. Now it depends. Molecules will have two types of force of attraction. I think you know about it. One is called force of cohesion. One is called force of adhesion. What is force of cohesion? Force between the same kind of molecules is called force of cohesion. And what is force of adhesion? Force between the different kind of molecules is called force of adhesion. So when you see the liquid is climbing up, that is this way, that means this kind of shape is formed. This is called concave shape, and this is convex shape. So in this case, we will find that the adhesive force will be stronger than the cohesive force. And out here we will find the cohesive force will be stronger than the adhesive force. That's why the curve is in the form of dip out here, dip, and this is elevation. The angle of contact out here at the point of contact is dipping, is convex shape, and this is concave shape. Normally this happens in Mercurian glass. If we have mercury and a glass rod we immerse, this will happen. And if you have a solid, and this can be anything, maybe water or maybe anything else, this will happen over there. The curve will be formed in this direction, like this. If it is a pure water, if it is a case of pure water, clean and pure water if it is, and you have a glass immersed here, glass rod here, then this will be exactly like this. There will be no, concave, no convex surface will be formed. It will be exactly like this. This time the value of theta will be exactly 0 degree. There is no curve only. No the theta value will be exactly 0 degree in this case. This is for clean water. But if the water is tap water, then the value of this theta will be 25 degree around. Then this kind of the value of theta will be 25 degree. If it is a tap water, that is not clean water. Okay. So in that case, we will get the curve in that shape. Okay. Now, this is about angle of contact. And angle of contact will be having, the shape of the curve will be like this, and like this. It depends upon the force of adhesion and force of cohesion. Now the next heading is pressure difference across a curved surface. Pressure difference across a curved surface. Pressure difference we can denote by delta P. Difference. Suppose we are having some liquid here. Inside the liquid we are having some drops, maybe bubbles here. It could be air bubble and this could be water here. This could be water. Like this. Suppose radius of this job is r. This is r. Radius of this job is r. Surface tension will be having tendency to minimize in area. Means it will cause the job to be contracting like this way. But we see just the opposite out here. What do we see? We see that the drop is expanding. The air bubble will be expanding there like this. It becomes bigger inside and then ruptures. Any kind of bubbles or any kind of drop inside a liquid surface will be increasing in size and then will be rupturing. Why does it increase in the size? You can see out here, atmospheric pressure is already acting on it. Atmospheric pressure is already acting this way. Atmospheric pressure on the bubble is acting. There is P0 is the atmospheric pressure. P0 is the value of atmospheric pressure. Atmospheric pressure. The value of which is normal value of which is 76 centimeter of mercury. But we find that and there is a force of surface tension also is there inside it. But yet this drop is expanding. That means it is expanding in size. Suppose the expansion in this radius is delta r, which is of course quite small change. The size increases just by a little bit margin only there. So with that is the delta r. Why this is expanding? Because this one is also giving a pressure, and this pressure, inside pressure, is more than the atmospheric pressure. The pressure given by this one is suppose P inside this. The P, because it's growing inside, then P must be bigger than P naught. That is delta P value will be like this. Delta P value will come P minus P naught. Delta P value is because it's growing inside, bigger, expanding. Okay, now we'll be finding the expression for delta P. This delta P is the expression we'll find. To find the expression, we'll be doing the work done in expansion. Let here work done of expansion. Expansion of this job. Work formula, we have force into displacement, right? Force into the displacement is this one because it's growing by this displacement delta. And force formula we have, because pressure formula we have is pressure is equal to force by area, therefore force will be equal to P into A. So here we will be writing pressure difference, that means pressure difference is giving a force over here. Pressure is these two different pressures are here, that is giving a force. And the force direction will be the direction of the greater pressure. The inside pressure is greater than the outside pressure. That is F is equal to be like a delta P into the area. What is the area of this? Area of the sphere will be 4 pi r square. 4 pi r square into delta. Mark this as equation 1. And here you will find that the new surface is created. This was the original side and the new sphere is being created. That is new surface area is created. We write here work done in creating new surface. That is W, and we know the formula W is equal to sigma into the area of the new surface created. I think this is the surface, new surface created over here, this one. So for that we will write the formula sigma into area. Area will be 4 pi, bigger one minus the smaller one. So 4 pi r plus delta r whole square minus 4 pi r square. I mean bigger square minus the smaller square, this area. Because this is the expansion in the area. This is the expansion in the area. New surface area is this one is created. New surface area is this much. We are finding the area of the new surface created. And formula we have W is equal to sigma into the surface created. This much surface is created. We'll take common sigma, 4 pi is common. We'll expand a plus b whole square formula. You get a square plus b square plus 2r delta r minus 4 pi r square. 4 pi is common, so r square cancel. 4 pi are taken out. We get answer coming at 4 pi sigma and delta R value will be very small because this delta R itself is very small. So when we square it, it becomes further very small. Just you can understand from this example. So delta R value is 0.001. The delta R square value will become how much? 0.000001. That is, it becomes negligible. Rest will be neglected. So this is the only answer left over. Into 2R into delta R. You can make a note since delta R is quite small. Delta R is very small, that's why you get delta R square becoming too small. This is equation number 2. Work done of expansion is same as the work done in creating new surface. We are creating a new surface there. So we equate the two of them. Therefore we write like this. Therefore, from equation 1 and 2, this will be equal to this. We will equate that delta P into 4 pi R square into delta R equal to this value. 4 pi sigma into 2R into delta R. Let us cancel delta will go. 4 pi will go. R and R will go. Making delta P the subjective formula, it becomes sigma by 2 and 4 will cancel. 2 sigma by R. This is level. This is the formula. The pressure difference formula will be excess pressure. Pressure difference is also known as, or you can write as, or this is also known as excess pressure. That is pressure difference. Excess pressure value becoming 2 sigma by R. And if you have to find the inside pressure, how much was the inside pressure? Delta P is P minus P naught. We write P minus P naught is equal to 2 sigma by R. Therefore, P value will become P plus 2 sigma by R. This will happen. Now, if this was we can write for a soap bubble. In soap bubble, 2 new surfaces are created. Soap bubble contains 2 new surfaces. We write like this. Delta P is equal to, we write 4 sigma by R. Instead of 2 sigma by R, for soap bubble especially we will be writing this. Delta is equal to 4 sigma by R. Instead of 2, because it contains 2 surfaces. The formula becomes 4 sigma by R. This is valid only for soap bubble. But if the shape of the bubble is like this way, just now the air bubble, the top surface was like this way, the top surface was convex. But if the top surface is like this way, then what will happen? Expansion will take place. The inside pressure and this will be going this way. That is, it is the same direction as the atmospheric pressure. That time this will become P plus. That time P naught will be bigger than this. P naught minus P will be equal to 2 sigma by R. In that case, this is for concave surface. Previous what I did know, this was for a convex surface. This was the formula for excess pressure for, you can write here only, for convex surface. But if the surface is like this, that time atmospheric pressure will be bigger than this. This pressure will be expanding it. So P, then the value of P will become now in that case. This was P naught. So this will become P naught minus 2 sigma by R. So we have to be careful what kind of surface it is. Convex or concave. So accordingly we will be making the correction. Here also P naught you have to write. If they ask you find the pressure exerted by the liquid surface here, then this pressure you find it, not the excess pressure, not the pressure difference. So that time P naught will be bigger. Just now P was bigger than P naught, but now P naught will be bigger than P, because this will be contracting off here like this and ultimately it will burst. Okay. So today we are doing this much. Next day We will do some problems and little bit only left over. The capillary action that I will discuss in the next class. Thank you.